Hello and welcome back to our discussion of shear turbulence. We're working our way through fronts right now. And in our last video, we went through some of the theories behind frontal turbulence. We looked at stability and shear associated with fronts. We also talked about how fronts are zones and also how they slope with height. What we're going to do in this video is talk about how to fly shear turbulence associated with fronts, and then also how to identify fronts on the upper level charts. So, what do you do if you're flying into an airport where there's a front located close by? Well, what you need to do is you need to be mindful of your approach or departure from that airport. In other words, visualize your airport, which runway you're going to take off on, and also visualize the location of the front. Now here we have a picture of a warm front that's south of the airport. But remember, warm fronts slope ahead and over the cold air. So at an altitude above this particular airport, you will find the warm front. And this is a two-dimensional cross-section through the front, showing how close the front is. It's 20 nautical miles south of the airport, this particular airport. And remember, our rule of thumb was 1 to 200, so 20 nautical miles is like 0.1 nautical mile up, and 0.1 nautical mile is 600 feet. So in this case, if there's a warm front just south of the airport, about 20 miles, then the front is going to be located 600 feet above the airport. And that can affect aircraft in the traffic pattern or approaching and departing the airport. So remember also that the winds shift across the front. So although we show the winds out of the north or out of the east or east-northeast on the cold air side of the front, north of the warm front, the winds behind the front are more or less pushing the front along at about 20 knots in this case. And remember that the warm air slopes up over the cold air, so those 20 knots of wind are going to also be found out of the south over the airport at altitude. So that's something you need to be concerned about when you're planning your departure as far as the performance of the aircraft when it encounters shear. But right now we're only talking about turbulence, so we won't discuss non-convective low-level wind shear until another lecture. So this is what it looks like visually or in a cross-section as you depart the airport. You'll notice that you have a headwind when you depart, but you'll have a tailwind at about 600 feet, and that does affect your performance. So here's some rules of thumb when you're flying turbulence associated with fronts. If you're crossing a front, usually your crossing time is very short. Remember that a front is approximately 50 nautical miles wide, the frontal zone, and that's about how long you're going to be seeing turbulence. So during that period of time, it's usually a short period of time, depending upon the type of aircraft that you're flying. It could be anywhere from 30 minutes all the way to maybe a shorter period of time, 10 minutes. So crossing the front, usually we are not too concerned with trying to avoid it. You're going to go through the front, you're going to get a shot of turbulence, and that's all you have to accept. But if you are paralleling the front, then you'll be in the frontal zone for a period of time if you're getting turbulence. So it would behoove you to change altitudes to get out of the frontal zone and in smoother air. And usually all it takes is 2,000 feet or 3,000 feet to get out of the turbulence. Usually less, but that's a safe bet, 2,000 or 3,000 feet. And then we talked about the things you look for when you're flight planning for turbulence with fronts. You look at the temperature gradient, you look at the movement of the front, and you look at the slope of the front. Here's a case where there's a strong warm front that's moving across the Dakotas, and ahead of the warm front the winds are pretty much out of the south. Behind the warm front the winds switch around to the northwest. Now this is in March, so temperatures are just starting to warm up, and you notice that behind the front they're into the 50s, and ahead of this warm front
their temperatures are in the teens, only 16 and 14 in some locations. So this is the scenario that we have at the surface. We've got cold air out ahead of the warm front. Temperatures start to increase as the front approaches. And behind the warm front, that's where all the warm air is. This is what it looks like at 925 millibars, which is about 2,400 feet MSL, so a little bit higher in the atmosphere. You can see that across International Falls and northern Minnesota, the winds are still out of the south or southwest. Across Bismarck, they're out of the northwest or west. So it looks like Bismarck is pretty much in the warm air. And down at the surface, or the lower layers of the atmosphere, International Falls, out ahead of that warm front, is in the cold air. Now this is a little bit higher, another 2,000 or 3,000 feet up at 850 millibars, which is about 5,000 feet. And the winds at International Falls are now out of the west, and at Bismarck, they're also out of the west. And what's happening here is the warm air that's out across the western Dakotas is moving up the warm front, and the higher you go, the more you'll get into that warm air. So there is actually warm air that is overlying the cold air at International Falls. And this is what you normally expect with a warm front. Warm fronts slope forward, out ahead, over the dome of cold air. This is the sounding for International Falls. They sent up at 0Z, and all these charts that we were looking at were at 0Z. And there are a couple of things that you can see. Number one is that in the temperature profile, the red line highlighted, you can see a really strong frontal inversion. So down low, you notice that the temperature at the surface is only 23. As you go up, temperature decreases with height until about 850 millibars, and then bang, you have a really strong inversion, and that's where the warm air is aloft. It's much warmer aloft, so temperatures increase with height. And that also shows up with the wind profile. Down at the surface, we said the winds are out of the south or southwest, but then when you get to about 850 millibars, the winds dramatically change to the west and even out of the northwest, and that is the warm air at altitude. So this is the scenario that's happening. This is Bismarck. Now Bismarck, you're back west, and there is no dome of cold air. You're in the warm sector of this warm front, which means that the entire atmosphere is warm, and that shows up in the sounding also. You notice that there is a little bit of an inversion at 700 millibars, but that's not a frontal inversion. That's caused by high pressure sinking, air sinking, and producing a cap. And we talked about that in the convective turbulence section, where you have this capping inversion that's usually caused by subsidence or sinking air. So that entire column of air is actually warm. And the wind profile shows that the winds don't really change much with height, an indication that there really is no change in temperature throughout that layer. So that's a little bit about warm fronts and cold fronts, looking at fronts and how they cause turbulence and how you can find them by looking at soundings and looking at upper air charts.